Yeah, I will silence.
Daryl's just doing this as well.
Yeah.
Good morning, everybody. Thank you for joining us on this glorious day in the northeast. The sun is shining, but we've got a couple of hours this morning with our friends at Zennio UK to go through some HVAC KNX controls using Zenio equipment. I've had a preview of what this is all about, and there's some great info in there that'll definitely help you guys. So look forward to it. Javier will explain in a moment. The session's broken up a little bit to keep you guys involved if we can. But from me, thanks for joining Zennio UK and my KNX store today, and the last webinar in the series. It's been great to have the guys along, giving some of their knowledge out, and look forward to getting going on this final one. Steve, are you okay to say?
Yes, I'm here. Good morning, everybody. Steve Lucas from my KNX store. Those that don't know me, thank you very much for joining us on this Friday morning, hottest day of the year. We'll try not obviously to keep it too long, but of course, heating, ventilation, and air conditioning are obviously key elements of what we all do in the KNX world, but probably the one that we possibly least understand fully. So we're really hoping that you can get some really good knowledge from today. We can never say we can know everything about all aspects of heating, ventilation, air conditioning, heat recovery. However, you know, we've got the right product set here. We've got the right people behind us. We're all behind you. So please do sit back, enjoy, and I'll hand you across to Javier.
Thank you, Steve. Thank you, Paul. Welcome, everybody. Well, thank you to my KNX store for putting this together, this fabulous series of 5 webinars so long. Today, last day of July, will be our last webinar of this series, and I'm actually looking forward to doing some live training at my KNX store premises whenever that's possible. So I'll be sharing my screen and we will get started in just 1 second. So as Paul and Steve mentioned, we are going to see a bit of HVAC. I will try to keep it probably in 1.5 hours, 2 hours. There's a lot of things to cover. Sorry, a lot of things to cover, a lot of things to go through. So actually, the course will be divided in 3 parts. We will be seeing preliminary concepts, a bit of HVAC systems and thermostatic control, control solutions, so the valve parts and controllers, and then the last part will be Zenio thermostats in how to configure and how to work with thermostats. And after each of the parts or each of the lessons, we will have a Q&A, and this way we can have, I would appreciate if you can write in the chat your questions. Vidar or Steve or Paul will be trying to answer them. And of course, during the Q&A after each part, I will try to go through them as well. So I said this should take some 1.5 hours, probably 2 hours. Hope you enjoy. So to start with, preliminary concepts. Well, HVAC, as Steve mentioned at the beginning, heating, ventilation, and AC systems. So climate or climate control, however you want to call that, what is usually referred as HVAC. So we are covering air conditioning systems and heating solutions. Sorry, sorry about that. So in terms of air conditioning, there are basically 4 ways or 4 systems inside air conditioning. We have split systems, which can be single and multi. This would be the common AC unit you can see outside of the wall. VRV, which stands for variable refrigerant volume or variable refrigerant flow. And VRV and VRF is actually the exact same thing. VRV is just a registered name by Dakin, who invested the system a long time ago. And then all the other brands, because the name VRV, variable refrigerant volume, was registered, they came up with variable refrigerant flow. And most recently with hybrid variable refrigerant flow. This is a type sorry, of multi-split system in which one unit produces heat or cold and then distributes the heat or cold to multiple systems. Then we've got thoning, which in thoning you have one unit producing heat or cold, sending air through different conducts, and then you just control grills at the end of the conduct to leave that heat or cold enter the room. And then we've got fan coil units, which are, as the name says, it's just a fan behind the coil with either hot refrigerant or a cold refrigerant, and the fan putting air through the coil so that the air gets hot or cold, and then putting it into the room. So that's basically the four big families inside the air conditioning: splits, VRV or hybrid VRV or VRF, thoning and fan coil, and each of them we will be covering how to control each of them in the controller's part. Then we've got heating solutions. Heating solutions involve mainly, of course, AC can produce heat, so you could have AC included in heating solutions. But in heating solutions, we will be saying, or we will be referring as heating solutions when we speak about radiators and underfloor heating. The main difference between using or controlling a radiator and underfloor heating, I'm not going or not trying to go into a depth explanation of each of the systems in HVAC, just trying to mention some particularities of them. So the main difference between radiators and underfloor heating is radiators work on the principle that they produce a very big temperature difference, while underfloor heating works on a very low temperature difference. So with radiators, you have a bit more inertia than in underfloor heating systems, where you have probably a radiator somewhere in between 50 to 60 degrees, producing a very big difference with the air in the room. And that difference, that temperature difference provokes the exchange in temperature. So because it's very big, it's heating the room. Because it's very hot, it's heating the room. While underfloor heating, it's because of the surface. So the principle in underfloor heating is you probably have underfloor heating somewhere over 20 something. You might want to keep that below 30 degrees. And there's, depending on the country, a lot of regulations regarding underfloor heating, and there's a maximum temperature that changes in every country. But the principle of working is it's a very big surface and there's a very small temperature difference. So the exchange of temperatures is provoked by the big surface rather than a big temperature difference. And in heating solutions, we control, in radiators and underfloor heating, what we control is a valve opening a circuit that goes either to a radiator or to the underfloor heating. We'll get into the valve control in a second, into the best way of controlling each of them in a second. So thermostatic control is what controls how the systems are turned on, off, or bigger. You want to produce a bigger temperature difference, or you want to have, so with thermostatic control, what you do is you turn on and off the systems and change some of the variables in the systems. There are basically two ways of controlling inside the KNX world, which are not very different from if you've studied control systems. Thermostatic control is basically a PI system where the system gets some inputs and produces changes internally, and then gives an output with information to what the system has to do. So we will be seeing 2 points with hysteresis, which is the current one you have in your screen. And then we will be seeing PI control or PWM. 2 points hysteresis is the most basic thermostatic control. It's recommended for low inertia systems. So basically to control AC units, for example, where you have not only a temperature difference, but because of the nature of that difference of convection, you have within an AC system, for example, you have air or cold or either cold or hot air getting into a room. So the exchange in the air is quite fast. The change in temperature in the room is quite fast. That happens very fast. So, and that's why 2 points hysteresis is very useful in systems with low inertia, which again would be AC, for example. The parameters to be defined in 2 points with hysteresis are just an upper and a lower hysteresis. You can see in the example in the graph here, this would be a system that where we are trying to heat a room, and we're trying to achieve 25 degrees. So 25 would be the set point temperature. So say we part somewhere from 22 degrees, we want to heat the system, we want to heat the room. So we turn on the system, and I'm not getting into what temperature we're putting in the room, just we turn on the system, and the system starts heating the room. Because it's low inertia, the second we turn on the system, it starts heating the room, because in an AC, for example, in the moment we turn on the system, it's pushing hot air into the room. So we would have then the room is getting hotter and hotter and hotter and hotter. And because our set point is 25 and we have to find an upper hysteresis at 26 degrees and a lower hysteresis at 24 degrees. So 1 degree over set point would be our upper hysteresis, and 1 degree over set point would be our lower hysteresis. And that not necessarily has to be the same thing. So you could have upper hysteresis in ½ a degree and lower hysteresis in 1.5 degrees. And you can change that, you can play with that depending on the system, depending on the particularities of the room you want to hit. For example, depending on whether it's heating or cooling. So you probably want to have, in a system where you're heating, having the upper hysteresis a bit lower, and in a system where you're cooling, having the lower hysteresis a bit closer to the set point temperature. So what it is doing here, what 2 point hysteresis control thermostat would be doing here is turning off the system whenever, so the second we turn on the system, it starts heating the room. You can follow the line. I'll just try to draw that somehow. Yeah, so we are starting heating the room. That would be that, heating the room. We go through our lower hysteresis and we don't turn off the system. It still goes on because it's low inertia. And when we reach the upper hysteresis point, you can see the system turns off because we are hitting. And because it's a low inertia system and we are not pushing any more hot air into the room, the system then, let me just put that in blue, the system starts to cool down because it's been turned off. It's been turned off, still cooling down, and now we get to turn it on again. And it's just repeating this cycle. So because it's, again, low inertia, I'm turning on the system again. It's on, and in not a very long time, it will start to heat the room up again. And it will be heating all the way until here. And then again, so that's the principle of 2 point hysteresis. So that's why it's so simple, because it's based on systems that will produce changes in the room really, really fast. So when I turn on the system, I immediately start to produce a change in the room. And when I turn it off, then the room goes back to its normal state. And that way, I'm keeping the temperature or the temperature in the room at somewhere, not always at 25 degrees plane, but somewhere around 25 degrees. Inside KNX, the control type or the object you would get in a KNX thermostat with 2 points of hysteresis is usually 1 bit, because you are just turning the system on and off. If using AC, for example, and where you want to define also, say, the fan speed, then you could also define internally, depending on the temperature difference, use more, bring the fan speed up or down. So, but that's not something to do with the thermostat itself. So that's something you would define the thermostat on with 2 points, and then when configuring the fan coil unit or the AC unit, you would say, okay, if the temperature difference is from set point to what I want to get is over 2 degrees, I want maximum fan speed. When it's just 1 degree difference, then I want to turn that that fan speed low to a minimum, for example, to medium level. But it's 2 different parts of the control. So, and now we are focusing on the thermostat control. So the thermostat will just send turn on, turn off, turn on, turn off, turn on, turn off in 1 bit. So then another way of controlling is via PI continuous or PWM, which means pulse width modulation. It's basically the same thing, or the principle is the same. It's a PI controller. PI controller requires 2 parameters to be defined, which are the temperature and the time, and that's what temperature difference your system can achieve in a given time. Say, for example, on the floor heating from off to on. So if the system is turned off and then you turn it on, you might define that temperature difference in a given time somewhere around 5 degrees in 4 hours. And that's not to be followed blindlessly. That's not just 5 degrees in 4 hours always. That's just a value, a reference value. Of course, it depends on the system. It depends on the temperature you are producing hot water for the underfloor heating, for example. It depends on quite a lot of parameters you want to check in your own installation. But these are the 2 parameters you define in the thermostat. What temperature difference you can achieve in a given time with this system. And you also define a PI cycle time. This is the time in which the cycle will occur. I'll get to this in a second. This is recommended as opposed to 2 points with hysteresis. This is recommended to be used with high inertia systems. So this would basically be any device that's not putting air into the room. So usually, again, we are speaking on general terms here, usually radiators and underfloor heating would be high inertia systems because they take a long time to produce changes in the room. If you turn on an underfloor heating, for example, if it was off and you turn it on, it will probably take 4 or 5 hours to start heating up the floor. So you can imagine just the time it will take for the system to start producing an actual change in the room. And that's what we call high inertia. You're not pushing air into the room. When you push air into the room with an AC system, you are putting air in and taking air out. So that's why the change is so fast, because you are putting cold air in and taking the hot air out, for example. But when you are using underfloor heating or a radiator, you are not putting any air in the room, so there's no air actually coming out. And that's what we refer to as high inertia. It takes time to produce those changes. Again, parameters to define in the thermostat are temperature change produced in the room in a given time, PI cycle time, which is the time every calculation, or the time it takes every calculation to be made again. And the control type in the answer, which is the difference between the PI and the PWM, is the answer they give. So PI continuous will give 1 byte in percentage. That's, for example, to control a valve, a 3-point valve, where you can control whether the valve is completely open or closed. Where you can control intermediate values, and you can say, okay, open the valve, but don't open it completely, just open to a 50% or to a 60%. So the control you are doing with a PWM is actually how open the valve is. And ideally, with a PI continuous, you would have, if you have a valve where you can open it to a 60, 70% or 20%, whatever values in between it can go. Ideally, with a PI continuous, you would have a value where the valve is stuck at a 30%, say, because that value would define a temperature for an underfloor heating system, for example, where the floor stays. If you want to achieve 23 degrees in the room, you can have the floor at 24.7, for example. And again, this depends on the particularities of the project or in properties of the floor itself. But you would have, ideally, if the valve is, okay, 20% open of the valve, that's 24.7 degrees in the floor, and that's 23 degrees in the room. So ideally, in a world where there are no external factors, with a PI continuous, you would have 20% open valve all the time. And that's where the PI continuous then actually takes, is useful, sorry. Because there are these changes, and there are these, you probably open a window, so it's getting colder in the inside, and the PI continuous is calculating that new temperature difference, and that's where the PI cycle time gets in. Every 15 minutes, for example, or 30 minutes, or whatever time you define, depending on the system you're using. This is something many times given by the producer of the underfloor heating system, or that radiator system, or the guy who actually, or the installer of the underfloor heating or the radiator, so the HVAC expert. And that's every 15 minutes. If you define a 15 minutes PI cycle time, you will be getting a new calculation. So depending on the changes that have occurred in the system in the last 15 minutes, the PI will give a new value. Say with what we had before with this 20% is 24.7 degrees in the floor, and then you open a window, so the room gets colder, and the PI will get this information, this new temperature in the room. The room is now not 23, it's gone down to 22. So there's been 1 degree difference, and depending on the parameters you've defined, the PI will calculate, okay, now I have to open not to 20%, because I have to gain 1 degree. I have to open the valve to an 80%. And that's what the PI will be doing. And the principle of the PWM is the exact same, but it's to be used with systems that go on and off. So no intermediate values, just on and off. But the principle is the same. The principle is, okay, I want to open the valve at 50%, but I've got a valve that opens either to 100% or closest to 0%. I don't have intermediate values. I have to open it or close it. I cannot decide whether I cannot decide to have it on a 50% or 70%, just open or closed. So the PWM is converting that 1 byte signal into a 1 bit, and in the given time. So say you've got a PI cycle time of 50 minutes, and you had a PI output of 50%. So what the PWM does is, okay, because I've got 15 minutes PI cycle time, and I've got a 50% answer from the PI controller. So what I do is I will open the valve for half the time of the 15 minutes. So for 7 minutes and a half, that would be open, and I will close it for the remaining 7.5 minutes. And that will give the valve to be open for 50% of the time and closed for 50% of the time. In the next iteration, so in the following cycle, the PI will say probably, okay, now you have to go to 80%. Then what the PWM will do is, okay, I have to open 70% of the time, and then the remaining 30%, the valve will be closed. And that's what we can see here in both of these. This is a PWM where you have 50% PI response. So I want to have the valve open for 50% of the time. So I turn on the valve during 50% of the time. And then, so my time, my PI cycle time would be the 15 minutes we were setting before, and that's on. And then for the remaining 50% of the time, so 7.5 minutes will be off. And again, after in the new cycle, because the answer is still 50%, I will open for 50% of the time and close. So the PWM is the same principle as the PI, just giving that answer in 1 bit, converting that to 1 bit on and off object instead of having 1 byte 50% value, for example. So that was the preliminary concepts, and as said, I didn't want to stay too long into that. I think the controllers are probably a bit. Let me just get the chat in case there are any questions. Yeah, sorry. So I don't know if there are any questions so far. Again, this was just a brief introduction of what systems we are going to control. That was AC, splits, fan coil units, VRV, or stunning, and a bit of introduction to the heating systems, radiators and underfloor heating, and then saying how we use whether we use two-point hysteresis thermostat or PI continuous or PWM. So I don't see any questions so far.
No, I can't see any questions. If there's any questions, guys, just write them in the chat. But hopefully everybody's following so far and are okay with that. Yeah.
Okay. That's good. We haven't got not anything very complicated so far. So now we are going to see the control solutions, or the involved parts that take part in a control solution. We've got thermostats on the one hand, and we've got controllers or interfaces on the other hand. Just to mention, thermostats are logic. So what we were saying a second before, PI, PWM, or two-point hysteresis, that's just a piece of logic. It's not an actual device. It's not necessarily a SET35, as you can see here. So this is a user interface of a thermostat, but it's not a thermostat itself. The thermostat itself can be inside the SET35 or inside the heating box or inside any other device. Actually, a lot of actuators or heating actuators in Zenio have built-in thermostats. So you can actually define a thermostat inside an actuator, inside a heating box, for example, which is the one we've got down here, or inside the SET35, but it's not necessarily in the SET35. That's a bit different with almost any other manufacturer I've seen in KNX, where a thermostat is a thermostat and looks like a thermostat. And you would, if you had something like a SET35, that's a room controller, that's got a thermostat built in, and that's got the user interface for the thermostat built in. But you cannot have the thermostat elsewhere. With Zenio devices, we treat thermostats as a piece of logic, as an independent block of logic that can be either on something that looks like a thermostat, which would be, again, the SET35, or in a heating box. Heating box has a thermostat, so we just build the thermostat in the heating box, and it can be controlled from any other device. So you can turn it on, off, change temperature, whatever you want to do outside of the Z35, you can do it into any other device. You might find that useful in a lot of projects. If you want to define your user interface in a different way and just use the thermostat logic behind it, you want to have a centralized, all the thermostats in the same place for whatever reason. For example, it's useful to have them in the manifold where you can install the heating box and just have that in the manifold or near the manifold. And the thermostat logic would be there. And in case something, you change your user interfaces, you can still have that thermostat logic running in the manifold. So it's very useful to have thermostats or to treat thermostats as independent or completely independent logic blocks in the KNX industry. What thermostats do is they, as we were saying before, they analyze information from the environment, they get those inputs, and they give some output, whether it's a 1 bit in a 2-point hysteresis, 1 bit in a PWM, or 1 byte in in a PI. And what they do is they send orders, these outputs to the controllers or to the interfaces. Say what we were saying before, a thermostat PI receives information from the environment, says, okay, the room is getting colder, I have to open the valve a little bit more. My previous answer was 20%. It analyzes not just the previous answers, but all the answers before that. It says, okay, for the last hour, I've been sending 20% all the time. Now there's, for some reason, external reason, there's a temperature difference. Now the room is getting colder, so I have to open the valve a bit more. And let's go, if I have to make 1 degree change, I'm going to go to an 80%. So it's sending that 80% to another device, to the device where the valve is actually connected. So the device can produce a change and say, okay, I have to open the valve a bit more. And I'm not getting into how that is done right now, but for example, that can be done with a SATA channel. And say you've got a valve that takes 20 seconds to open and you are in a 20%. So you know you have 60% of the time left to open, and you would just, okay, open for 12 more seconds. So you are actually open to the 80% that is required by the thermostat. And the controller or the interface is the device that is actually doing this. So the thermostat is just sending to the controller, open a bit more, open to an 80%, and the controller is then producing the change, whether that's a relay, an electronic relay, whatever that is, producing that change and saying, okay, go to that 80%. And if it's an interface, what it does, it's just translating that order. So an interface would be just a translator between the KNX system or the control system, but because we're in KNX, the KNX system and the AC unit, for example. You can see here on the right, that's a click FJ. That's a direct interface from KNX to Fujitsu units. And that's almost anything in the family of Fujitsu. So what an interface is doing is just getting that, okay, send say the thermostat says, I want to get 25 degrees or want to turn on the unit, and the interface will just say, okay, it will translate the KNX 1 bit on to Fujitsu or Toshiba or Daikin or whoever that is, turn on the AC unit, and that will be turning on the unit. But these are basically the two parts involved. We've got a thermostat, which is the one responsible for analyzing the information and sending the orders. And then we've got the controller or the interface, which is the device actually producing the changes or translating that into any other language. Now we get into the controllers themselves. We've seen the thermostats at the beginning, or a bit of the thermostats in terms of what we can define in the thermostat, or what parameters we should define in the thermostat. And now we go into the controllers themselves. So a fan coil controller, fan coils as said, is a system where you have a coil and a fan. So you just bring that together in fan coil. A coil with either hot or cold water, which would be a two pipe. So in a two pipe, you've got in the same coil, you've got either hot water or cold water. Sorry, I'm saying water, it's actually refrigerant, whatever refrigerant that is, either hot or cold, and a fan putting air through it. Or it can be four pipes, in which case you would have a coil for the hot refrigerant and another coil for the, one coil for the hot refrigerant and another coil for the cold refrigerant. In thermostats, in fan coil units, what you can control is usually the valves and the fan speeds. And there are different ways of controlling that, and you can combine what you're now seeing on the screen almost in any way. So you could have valves that are operated just via relay, so open, close. Valves that are operated via a 0-10 volt contact, 0-10 volt, and that's called, well, I call that interface because it's just a 0 to 10 volt is just a control signal. It's not actually providing 0 to 10 volt to the valve, or not necessarily. So you get a 0 to 10 volt signal for control, and then you open the valve accordingly to that. Or you could also have dry contacts, again, interface into something that will actually open or close the valve. And the fan speeds in the same way, or in a very similar way. You can have them controlled by relay. So, and that, depending on the fan coil unit, would be independent relay. So say you have 3 different fan speeds, and you can go, okay, turn on channel 1, which would be a minimum speed, then turn off channel 1, turn on channel 2, medium fan speed, turn off channel 2, turn on channel 3, and that would be maximum fan speed, or cumulative, and that depends solely in the fan coil unit itself. And cumulative would be, okay, turn on output number 1, and that's minimum speed. Now add output number 2, that's medium speed, and add relay number 3, that's maximum speed, for example. Or again, you can have this interface with a 0 to 10 volt control signal, or again, dry contacts, and then there's a third-party device actually controlling the power sent to the fan. So, but either if it's a 2 or a 4 pipe, what you're controlling is basically the valves and the fan speed. The main difference in terms of control in a 2 pipe or a 4 pipe is that in a 2 pipe, you just control 1 valve, and in a 4 pipes, you control 2 valves, 1 for hot and 1 for cold refrigerant. The device you can see here, for example, is Maxim Box Hospitality. This is a fan coil controller. You can see down below here, this is meant to control on-off valves. So you would have either 2 or 4 pipes. So 1 valve for hot, 1 valve for cold, and then you've got 3 fan speeds. And then inside the device, in parameters, you define whether that's independent relays, 1 at a time, or cumulative relays. It also has got inputs and some spare outputs, but we're not seeing that right now. Let me just close that. So some of the fan coil controllers in the Zenio family, and again, fan coil control is just a matter of logic. If you are controlling a fan coil with relays, it's just a matter of defining how the relays are going to work together. So we actually in Zenio, we build fan coil logic, fan coil control logic in a lot of our devices. For example, the new family, the all-in box, which has just recently been made available for the general public, or for the integrator public. We've got all-in box 1612 and all-in box 88. This is a quite a wonderful product in KNX. It's a power supply unit plus an IP interface. It's got 16 or 8 outputs and 12 or 8 inputs. So it's quite capable device, and it's still a full KNX device. And in terms of the fan coil logic, it has a built-in fan coil logic, so you can define the channels to work as individual channels, as SATA channels, or you can configure them to work as fan coil controller. You would have, for example, in the 1612, you would have up to 2 fan coils, either 2 or 4 pipes. And in the all-in box 88, you would have just 1 fan coil, 2 or 4 pipes. And that's because 4-pipe fan coil with 3 relay fan speed actually takes 5 outputs. So that would be 3 for the relays, 1 for the hot, and 1 for the cold. And yeah, again, in the all-in box, you can only control fan coils, just to mention, which are controlled by relays. So both the speed and the valves are controlled by relays. Then we have some other multi-purpose actuators with fan coil logic. We've got the mini boxes 40 and 45. These have built-in fan coil logic because it's only 4 outputs. You can control either only a 2-pipe fan coil with 3 relays for the fan speed. There's also Acting Box Max 6, which is a bit different because it comes from the old Zenio family, but it's still available. And it works in a bit of a different way because it has a dedicated fan coil application program. So you will see, if you go to the Zennio website and you visit Acting Box Max 6, you will see there are 3 different application programs, one of them being the fan coil application program. And it can control 2 or 4 pipes plus 3 relays for the fan speed. The Maxim Box family, both 8 and 16 version 3. Version 3 just stands because it's the new family. It has, but it's basically, in terms of the fan coil configuration, the same thing as the Maxim Box 24. And they can both, all of them, the Maxim Box 8, 16, or 24, they can control fan coils with 2 pipes and 3 relays. That means you don't, because it has the fan coil logic, the fan coil control logic built in, you don't have to make that logic yourselves. So you just select, when you configure the outputs, if you look at it, you will have, how do you want to configure this block? Is it independent outputs? Is it a SATA channel, or is it a fan coil controller? And you select a fan coil controller and you already get all the logic for the fan coil control is in that device, and you can configure it directly there. And of course, so we've seen the all-in box, we've seen the Maxim boxes and the mini boxes, which are multi-purpose, and then we have a specific fan coil controllers. So we've got, again, the Maxim Box Hospitality, which is probably, or it was when before we came out with the 0 to 10 volt controllers, the most flexible of them all, because it allowed 1, 2, or 3 relays for the fan speed control, and it can control 2 valves, so 2 or 4 pipes, and 2 on off, or a 3-point valve with intermediate values. Then we have Maxim Box Fan Coil, which is 2-channel 2 pipes or 4-channel 2 pipes. So Maxim Box Fan Coil is just for 2 pipes with 3 relays, and the difference between them is just the number of fan coils you can control from them. So Maxim Box Fan Coil 2-channel 2 pipes would be for 2 fan coil units, each of them with 2 pipes and 3 relays for the fan speed. And the Maxim Box Fan Coil 4-channel 2 pipes is just to control 4 fan coil units, each of them with 2 pipes and 3 relays for the fan speed. And then we've got the Maxim Box Fan Coil 0 to 10 volt fan and the 0 to 10 volt valve. The main difference being that the 0 to 10 volt fan is meant to control, with the 0 to 10 volt output, is meant to control the fan speed. So it would be a 2 or 4 pipes fan coil controller, and it can control then the fan speed in a 0 to 10 volt with a 0 to 10 volt control. And if configuring two, if configuring, sorry, just wanted, I have to catch my breath a little bit. So 0 to 10 volt fan, 0 to 10 volt output for the fan speed, and it can control up to 2 fan coil units. And the maximum box fan coil 0 to 10 volt valve is meant to control 0 to 10 volt valves and then control the fan speed via relays. And depending on how many fan speeds you have, you can then, for example, with the 0 to 10 volt valve, you can see here, you can have 1, 2, 3, or 4 relays for the fan speed. If you just use 2, then you have 2 spare outputs, so you can have some spare outputs. And as you can see here, something interesting again, thermostats, both the maximum box fan coil 0 to 10 volt fan and 0 to 10 volt valve, they have 2 built-in thermostats. What I was back to what we were saying, or what I was saying before, thermostat is not just the device you can see as a thermostat, it can be built in the controller. So in this case, the maximum box fan coil 0 to 10 volt fan and 0 to 10 volt valve, they both include 2 thermostats. Just to mention, the all-in box also includes 4 thermostats plus 4 hospitality thermostats, but I will not get today into the hospitality thermostats, just because they are meant to work with some objects in the hospitality environment, which are in hotels, for example, where you have check-in, if the room is sold or not, and it wouldn't make sense to use that in a residential, neither a commercial development or a commercial project, because it's very specific for hospitality, for hotels, basically. Now, the interfaces, as I said before, so what we've seen so far, or the controllers we've been seeing so far, are meant to control fan coil units, where you directly operate the valve and the fan speed via relays, via 0 to 10 volt, or via dry contacts. And now we get into the interfacing. So this is actually translating from KNX to some other language, which would be the language spoken by the AC unit itself, or, well, yeah, basically the AC unit, and also if it's a production system such as Altherma or Mitsubishi Ekodan, we also have interfaces for those. But an interface is just translating the orders. It's not producing a relay change. It's not operating a relay to say, open the valve, close the valve, turn on the fan speed at medium level or at maximum level. So an interface is doing something different. An interface is translating from KNX to the Daikin language, the Panasonic language, the Toshiba language, whoever that is. We've got interfaces for Daikin, either residential or commercial units, and Daikin Altherma, the Click DA. In its last version, we are also with the Click DA. It's also compatible with Altherma 3. Interface for Panasonic, interface for Toshiba units, interface for Fujitsu, plus all the Fujitsu family, which General, Hayasu, and Fuji Electric. I think a couple more. Interface for Mitsubishi, so you would have Click Meet version 2 for the AC units, and Click Meet E for the Ekodan unit, which Ekodan and Altherma are, how to put it out, heat pumps which can also produce cold, so they are full production systems for hot water, heat pumps for an underfloor heating, and also can produce chill water or whatever refrigerant that is for fan coils or for an AC or for an AC unit. We've also got an interface for LG. And again, you can see how the names kind of refer to what device we are compatible with. So Click DD would be Daikin domestic, Daikin industrial or commercial, That's just how it's referred to in Daikin. Click PA, Panasonic, click TS, Toshiba, click FJ, Fujitsu, click MIT, Mitsubishi, click LG, LG. And also another way of interfacing is via IR control with IRC. Again, IRC is a device, it's an IR transmitter with two different application programs, which are actually 3 different application programs. Well, 4 different application programs, but you've got IRC Plus, and IRC Plus comes in 2 versions. That's just because in one version we couldn't bring all the devices together, so a lot of devices are in one version and a lot of other devices in the second version, but they both exist at the same time. And IRC Plus is, when using the IRC Plus, it's an IR interface where the IR codes are already in the device, in the IRC. So say you want to have the codes for a Daikin unit and you have the IR remote, you don't actually have to read those remote control, those remote strings, those IR strings, because the IRC Plus might already have them. So there is a huge compatibility table. There is a compatibility table for all of them, but the compatibility table for the IRC is quite huge. And what you do is you check your remote, your IR remote, and if that is included in the IRC Plus, you just select a parameter in IRC Plus, say parameter 125 is for the Daikin unit you're going to use. You just select parameter 125, and that's got the IRC codes already built in. And the second possibility would be IRC Open, which is for remote controllers which are not already implemented. So that would require recording the IR strings into the device. But again, for AC control, almost everything is included in IRC Plus. And if it's not, and you want it to be included, you can just let us know, send us the IR remote. We will capture the codes for you, include them in IRC Plus, and that way we make it available to everybody. If a fellow integrator over in Czech Republic then has the same unit or the same remote control you were using a year ago, he will not have to repeat the process because it's already implemented in IRC Plus. So we've seen fan coil control, we've seen direct interfacing, whether that's translating into the language of each manufacturer or translating to IR interface, to IR string. And now we've got phoning. In phoning is a bit of a difference with the above, in terms that you still have to control the AC unit when doing when controlling a phoning AC solution. So you have the AC unit on the one side. I forgot to mention with the interfaces. Interfaces work with the indoor unit. So communication with the indoor unit and the outdoor unit, it's something that they do by themselves. No need to control the outdoor unit. You just control the indoor unit. And the indoor unit, whatever you tell the indoor unit, then the indoor unit will communicate with the outdoor unit and do what they have to do. But control from the KNX side or from any other control system, that's not Daikin or Panasonic, or so any control system, any user control system is meant just to control the indoor unit. And then how the indoor and the outdoor unit communicate with each other, that's a different world. So all the AC interfaces are meant to work with an indoor unit, just with the indoor unit. And now, back to phoning. In phoning, you have to control 2 different things. You have to control the AC unit, whether that's a fan coil or a Panasonic split or a VRV, whatever that is. Usually it would not be a VRV because VRV is already working as a kind of multi-split. But whatever your AC unit is, you have to control that on one side and then control the air grills. So the phoning, what the phoning is doing is you have an AC unit producing hot or cold, heat or cooling, heating or cooling, and then sending the air through different conducts or through different pipes to the different rooms. And what you control in each room is just a grill that opens and closes or closes and lets the air in or doesn't. So the thermostat would actuate through the grill controller, and then the grill controller, which is what the thawing box 4 or 6 or the IRC again does, that logic is what will be controlling the AC unit. So here we would kind of treat the thawing box as the indoor unit. What we do, or what the thawing box is doing, is having that logic that communicates all tones together. And the thawing box, both the 4 and 6 can control up to 12 different tones in up to 2 groups each. Sorry, in up to 2 groups. So 12 tones in total in up to 2 groups. You can have one group, and one group, each group is what is actually one AC unit. So say you have one AC unit giving heating or cooling 4 different rooms, that would be 4 tones in one group. And then you have a second AC unit giving cold or hot air to 6 different rooms, that would be a second group with 6 tones. Now, the logic, what the logic of the thawing does is basically when you have everything closed, it's turning off the AC unit. When you open the first grill, it's turning it on. And then depending on the level, on how many grills you are opening, it will speed up or slow down the fan speed in the AC unit. That's basically the functionality. You can then define, okay, I want the last grill to stay always open, so you don't have any overpressure in the conduct, or I want to stay open for 30 seconds after the AC unit is turned off, or 1 minute, or whatever time you consider that is, that should be. And then also you can define, okay, when turning on the unit, so when all of them are closed, if I open any of them, I want it to open the grill first and not turn the unit after 20 seconds or 10 seconds have passed, something like that. So you can't work with them. And the thawing box is just doing that logic of, okay, I've got all of them open, so I want maximum speed. I'm closing 2 of them. I want to bring speed down to 50%. So that's the logic it will be controlling. Air grills generally are 12 or 24 volt DC with reverse polarity. And you can always also have 230 volt volt AC or 110 volt. So thawing can do the logic, and in terms of just referring to thawing, it can do the logic and then control the grills, but you can have thawing doing the logic. Say you have 12 tones, you could have 2 thawing box 6, just one of them doing the logic, and then the outputs work on a different block. They are completely independent. So you could have 2 thawing boxes, one of them with all the logic, and sending the order to all the 12 grills in the system. Now, very important with thawing box is to have actually, it will send the order to the grill. When the grill opens, it will send a response back to the thawing box. So that response is really important in the thawing box, because that's what will be defining the control of the AC unit. Both thawing box 4 and 6, 4 is for 4 grills and 6 for 6 grills, have either 12 or 24 volt reverse polarity control. Just quite easy to change from 12 to 24 volt. You can do that with your nail or with a screwdriver, but you have to do it hardware. And again, this is to work with reverse polarity, but you could, if you had 230 volt grills, you could have the thawing doing the logic and then sending the order to the 230 volt actuator, or to the relay actuator, or to whatever actuator you actually have controlling the grills, so where the grills are wired. And IRC is mainly the same principle. So again, we saw before there was IRC Plus in version 6 something and 8.12, I think. IRC Open, which is the one where you have to actually record the remote controls yourselves. And then there is IRC Zone application program. So it's a fourth application program for this device, which is just which just has the zoning logic. So it has the logic for all that for controlling 8 zones. Say you have 6 different rooms with 230 volt grills. So you could have the IRC with all the logic. Of course, you can write the logic yourself, and the IRC is just making this process easier, and it's just a device with the logic inside it, and it will be sending to the bus the orders of open and close, and then turn on the unit because I'm having demand on one room, turn it off because I don't have demand, change the fan speed because I have more demand or less demand. So that all is written in the zoning logic. Other than that, it also has logic to control the temperature. So it will, if you have a demand for 24 degrees, it will allow you to send to the AC unit a lower or a higher set point temperature, say because you know you have you lose 1 or 1.5 degrees in the pipes, so you want to offset that. So when you receive demand in cooling mode for 23 degrees, you actually want to send demand to the AC unit not in 23 degrees, but probably in 21 or 20 degrees to offset that loss of temperature you will have on the pipes. So we've seen all the fan coils or the AC units, the toning inside the AC, and whether that's combined with fan coil or an interface. And now we go to heating valves, basically underfloor heating and radiators. Heating valves can be controlled with relays, such as the maxim boxes or spare outputs in fan coil controllers or the all-in boxes. So you could control the heating valves just with the relays. Our recommendation, however, is to use a dedicated device such as the heating box, whether that's 230 volt or 24 volt. And there's a reason for that. So in a KNX relay, you will always have, first of all, that click, 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 click sound of the relay actually closing the circuit and opening the circuit. Other is that the relay life is limited. It's in our devices is usually rated for 10,000 switches or 10,000 cycles, opening and closing. So so when using, for example, an underfloor heating radiator and controlling a valve with PWM, we were saying before in PWM that you have in a very common PI cycle time for underfloor heating would be 15 minutes or 30 minutes. If you have that and you have PWM, you know every 15 minutes you have 2 switches because it's turning on and off the device. So the valve, sorry. So with the relay, that, well, you can make the calculation if you put that to 30 minutes, that would be 48 times a day. So just calculate the day, 10,000 divided by 28. And I'm actually making that now. 48, yeah, that's 208 days. So the life cycle of the device would, if say you have that on forever or always, you can see how in under a year you're probably reaching the life of the device, life cycle of the device. Will very probably last way longer than that, but you're already bringing the device, you're already testing the device into its life cycle. So you probably want to use not a relay or not a full relay, but an electronic relay. And that's where the heating box 230 volt or 24 volt come in. They have electronic relays, whether that's triacs or MOSFETs, depending on the version. So 230 volt has triacs, 24 volt has MOSFETs. So you don't have the sound. A life cycle is almost infinite. So because it's electronic, it's not an actual mechanical change, so it will not break. And so we just recommend, when using, although you can use the relay, of course, we always recommend to go for the heating box if controlling underflow heating or a radiator in a valve, or the valve of a radiator, because it will definitely last longer and you will not get the noise of the click, 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 click every 2 times every 15 minutes or 2 times every 30 minutes or whatever you configure there. So I set 2 versions, 230 volt and 24 volt, both in 4 or 8 channel, up to 5 valves per output, or up to the rated current, so 200 milliamps. Heating valves usually are somewhere around 40, 50 milliamps. So there's, you can see there's, it kind of matches the 5 in 230 volts. So 5 valves would be to 40 milliamps valves would be 200 milliamps, an inrush current of 2.5 amps. And in the 24 volt, that's a bit higher, 1 amp and 6 amps. You can see the difference with the actual relays. So the relays were, the relays in other devices are most of them 16 amp. And this, you can see the rated current is 200 or milliamp or 1 amp. So it's way higher because it's an electronic relay. But we definitely recommend always to use the heating box for controlling valves. Any questions so far? I don't see anything in the chat. Little activity today, I imagine. It's probably too early for all of this.
Yeah,
okay.
no questions yet again, so.
Okay, we will also be having a Q&A at the end, so so you can still place your questions at the end. Just to go through all of it so far, we've been seeing the main HVAC systems, AC, fan coils, a bit of the difference between the thermostat, how the thermostat logic, what the thermostat actually is, that it's logic. I want to make a good point here. It's logic, it's not, so you don't have to buy a Z35. For example, of course, if you buy a Z35, it's better, but you don't actually need the Z35 for the thermostat. You can have the thermostat built in a device in the electrical board, and then have whatever user interface you want to use with the thermostat at the back, or hidden from the user, and the user will think he's got the thermostat in his hand, but it's somewhere else. We've seen some of the heating solutions. We've gone through the thermostats, PWM, PI, 2-point hysteresis. We've also seen fan coil controllers, the interfaces, the differences between fan coil controllers, the heating solutions, and the thoning, a bit of the thoning there. So, and now we'll jump into the Zenio thermostat, into configuration, into how the Zenio thermostat works. Yeah, so again, I said before, and I insist, Zenio thermostats are independent logical blocks, which can be built in almost any Zenio device, or can be found in any Zenio device. Just to mention some of the devices which actually include thermostats, all the touch panels, Z41 family, Z35, and the upcoming Z70, they all have 2 thermostats, 2 built-in thermostats. All the capacitive switches, whether that's flat 55, all the TMD family, includes TMD displays, the one with displays and the ones without displays, they all have 1 thermostat. All the devices with inputs, so the Quad Plus with 4 inputs has 4 thermostats. The rail quad, which is 8 inputs, has a thermostat. Sorry. All the actuators that with inputs, so not only the devices with dedicated, sorry, and just to mention, not the devices with binary inputs, but the devices with analog digital inputs. So that's basically the Quad Plus and the Rail Quad 8. And all the actuators with inputs, minibox 24, 25, 45, the inbox, all of that, the maximum box 6, they all have 4 thermostats. The ones that have inputs, some of the fan coil actuators, as we saw before, the maximum box fan coil 0 to 10 volt fan and the 0 to 10 volt valve, they have 2 thermostats. The heating box, if it's a 4-channel, has 4 thermostats. If it's an 8-channel, it has 8 thermostats. And the oven box has the 4 thermostats I mentioned, plus the 4 hospitality thermostats, which are the ones meant for hotel projects. And again, you can use them. It's not anything you cannot do with the advanced thermostat and some logic, but it's just probably overcomplicated to build and configure, because a lot of things will make no sense at all. So why would you have a check-in object or a sold room object in a residential or a commercial project thermostat? So which is required in the hospitality thermostat. So you can open the oven box, check it, see what's inside, but you will see most of the things it has are definitely useless for most of the projects, which are not hotels. So again, the Zenio thermostat has, or every thermostat in KNX, but getting into the Zenio thermostat, the thermostat has some inputs, whether that's user actions, turning on off the thermostat, changing the mode, changing the special mode, changing the set point. So we consider that as inputs. Actually, this would be what in the ETS looks like, has the W flag, so you can send something into the device. Environment information, room temperature, if there's an alarm. So all of our thermostats, you can configure an object called window alarm, which is meant, it can be used with a window or it can be used with whatever 1-bit object where you want that to turn off the thermostat. And for example, in combination with the Z35, you could get something like a window opening and closing saying thermostat is off because the window is open. But anything that is an alarm or you consider an alarm in your project can be linked to the window object in the Zenio thermostat. And 2 room temperature sources. So all of our thermostats can take the room temperature from 2 different sources and combine that however. So it's either source A or source B, and then any combination in between, 25-75, 50-50, or 75-25. And then the thermostat analyzes this information with the parameters, according to parameters, whether it's 2-point hysteresis, whether it's a basic thermostat or an advanced thermostat, whether it's PWM, whether it's PI. It analyzes all that information we considered as inputs. Okay, I'm in comfort mode, my set point is 22 degrees, and the room temperature is 20 degrees, so I have to heat up the room, but because I'm in cooling mode, I cannot heat the room. If I'm in automatic mode change and I'm under the set point that's been decided to be used, then I can produce heating, so I will demand heating, and that output is what we consider a control variable. And we saw the control variables before at the beginning. Control variables can be either 1 bit for 2-point hysteresis, 1 byte for PI continuous, or again 1 bit for PWM. The good thing, for example, when using PWM is that you get both responses. So you will get the 1 byte object and the 1 bit object. In case you find that useful, or in case you want, it's actually very, very useful if you want to check the actual response from the thermostat. So you have the 1 bit object opening and closing the valve, and then you have in a display, in a user interface, you have the 1 byte object telling you, now I'm on 70%. So you know the valve is going to be open for 70% of the time. Very useful if you think in low values where you probably haven't seen the valve open because when you checked, it was already closed. And then you go to the user interface and see, oh, it's 10%. So it's just been open for a minute and a half, something like that. So very useful in all those scenarios to have the 1 bit object and the 1 byte object to use as information. So these are the outputs that the thermostat will provide: 1 bit for 2-point hysteresis, 1 byte for PI, 1 bit and 1 byte for PWM. Looking a bit at the scheme here, you can see how, okay, you can tell on off mode. So these are all the objects you will have, all the inputs you will have in a Zenio thermostat. On off, the mode, cool or heat, the special mode, comfort, echo, whatever the standby, whatever that is, set point as the user set point, and real temperature or room temperature. And again, this can be from 2 different sources. So you will have 2 objects in the ETS, 1 for source A and 1 for source B, and that's for every thermostat. So if you have a device with 8 thermostats in which you want to have each room temperature from 2 different sources, you will have in that full block of logic with 8 thermostats, then you will have 16 objects for room temperature. Source A and source B for thermostat 1, source A and B for thermostat 2, and so on. Then depending on that, it will analyze the information and provide the control variables. And control variables come in, well, I already mentioned you have 1 bit or 1 byte, or 1 bit and 1 byte with PWM, but you can define up to 4 completely independent control variables. A control variable for cool, a control variable for heat, additional heating, and additional cooling. And when you define additional heating and additional cooling, this becomes a complete new thermostat. So if you define any thermostat with additional heating, you define it will say whether it's 1 or 2 systems. And actually, it will allow you to define which is the main system and which is the secondary or the additional. You define everything in the first one, and then the second one comes as a completely new thermostat. So if you have PWM in system 1, you can have 2-point hysteresis in system 2, or PWM again, or PI in system 2. So completely independent thermostat. So actually, when you look at it, it's more like 2 thermostats within the thermostat. So you have, again, control variable for cooling, control variable for heating. You can have this in one object in case you have, for example, underfloor heating and underfloor cooling, and you know that's coming from the same place. You could have that as just one output. Whether you can configure, whether you want this to be sent on a cycle basis every minute or every something, whether you want them always to be sent, both heating and cooling, all of that can be defined. And again, additional heating and additional cooling. Thermostats, as Zenio thermostats, can be defined in 2 ways, basic or advanced thermostat. There's not a very big difference, or actually there is no difference in the way they work on the PI, on the 2-point hysteresis, or the PWM. That's done exactly in the same way, both in basic and advanced. So if you select a basic thermostat, you still have PI, PWM, 2-point hysteresis. You still have all of that. And the difference between them is basic. The basic thermostat has no special modes. So it's either on, off, and heating, cooling. And it has a very simple automatic change of mode defined by a set point for cooling and a set point for heating, which is what you can see here in the screen. And let me get that in probably green. So this would be the thermostat is in cooling mode, and you have selected automatic change of mode. Thermostat is in cooling. It's cooling the room, however that looks like. And when it gets here, when it gets to this point, below the set point for heating, it's not the set point, sorry, it's the set point for heating. So there will be two different set points, one for heating and cooling, when you have a system with automatic change of mode. And when it gets below the set point for heating, it will start heating. It will go into heating mode and start heating the room. And then again, when it goes over the set point for cooling, it will go again automatically into cooling mode. And sorry, let me just erase that. So, but of course you can define, you can select not to have an automatic change of mode. So in that case, it will just look for a set point and try to get or reach that set point. If it's in heating mode, heating the room, and if it's in cooling the room. So you can define whether you want or not the automatic change of mode, both in the basic and the advanced. And then the advanced has a special modes with absolute or relative set points, which are the two diagrams we can see here. And it also has the advanced automatic change of modes, which is a bit different to the previous one, to the one we can see up here, because it will depend not on, it will have not a set point for cooling and a set point for heating, but a set point for each of the modes in heating and cooling. So just to go a bit through it, when you define an advanced thermostat with absolute set points, you have, and again, let me just paint a bit here. You will have, okay, I define my set point for cooling and heating in the comfort mode. And then I have an offset for standby and an offset for economy in cooling and an offset for heating and an offset for economy. Sorry, an offset for standby and an offset for economy in heating. And if you do that with relative set points, what you have is one basic set point. So here with absolute, you have one set point for comfort in cooling and one set point for comfort in heating. With relative set points, you have one basic set point, and then you have an offset for both comfort, heating or cooling, an offset for both standby, heating and cooling, and for both for both economy, heating and cooling. But you have two set points or two basic set points, one from comfort in cooling and one from comfort in heating with absolute set points, and one basic set point, and then all the offsets from there in relative set points. And of course, the automatic change of mode will depend on the mode you actually are. So, so if you were in a standby, then as you can see, am I still with the pencil? Yeah. If you were in heating mode standby, the room will be heating all the way heating until the standby cooling set point is reached. So you can see there's an 11-degree gap here because we are in standby in this example. So we would be here. I'm in standby mode. I have selected standby and automatic change of mode with an advanced thermostat. So what I'm doing is I'm heating because I'm in standby all the way until I get to the standby cooling set point. And then if I reach the standby cooling set point, I'm then cooling all the way until I reach again the standby heating set point under that. Sorry. But again, the difference in the way they treat the PI, the PWM, or the 2-point hysteresis is the exact same in both of them. So the basic set point, the basic thermostat is not really basic. You can still do a lot of things with it. It's definitely very useful for residential and commercial buildings. The main difference you will be getting with the advanced one is the capability of using special modes, as said, comfort, standby, and economy. But that's the only difference. Now, I introduced just before the additional cooling and heating. This is to be treated as a completely independent thermostat inside the thermostat. So if you have, you define one system, say underfloor heating would be the main system, and then AC would be the second system. What the device is, and you are heating, you want to heat, and you define a band or an offset to start the second system, to start the additional heating in that case. What the system is doing is, okay, you have defined a set point of 22 degrees, and the room is currently at 20 degrees, and you have defined a band of 3 degrees, then only your main system will operate. But when the system goes below, if you have that band of 3 degrees, sorry, just I didn't notice the example had actually, so if we had a set point temperature of 23 and an additional heating band of 2 degrees, when I go below those 2 degrees, I'm turning it on. In this case, you can see from 18 to 23, we have a 5-degree difference. Our band is 2 degrees. So we want to turn on both systems, underfloor heating, and because underfloor heating we know will take quite a while before it actually starts heating the room. Then, so we turn on the AC as well. So we are hitting from 18 degrees and we get the room to 21. And the second we get the room to 21, the AC unit will stop working, will go off because we have defined it as the second system. And now, if the underfloor heating has had time enough to heat, to start heating, then it will follow a more progressive curve. So this is usually very useful in combining two systems. One low inertia system, such as an underfloor heating or a radiator, and one high inertia system as an AC, where you want to have this at the beginning, a very fast change in temperature for the first 4, 5, 7, 10 degrees, whatever that is, but you want that to change fast. And then you want to have a more comfortable control or a more comfortable temperature, not with AC, for example, or with 2-point hysteresis in a room where you have, in the summer, for example, if it's a very hot summer, you will see it's turning on, turning off, turning on, turning off, and you will be getting that temperature difference depending on the 2 points on the hysteresis you have defined. So if you have defined 2 degrees different, or 1 degree lower hysteresis and 1 degree upper hysteresis, you will have up to 2 and a bit more than 2 degrees difference in the room all the time. So you probably want to have a low inertia system controlling that, or a smaller 2-point hysteresis band controlling that. But if you go into the summer, say you go into a summer house where you haven't been for a while, and it's 28 degrees and you want that to go to 23 degrees, and you have underfloor cooling, so you want to bring that down from 28 to 25 very fast, and then 25, which is bearable, and then you want to have the underfloor cooling working, or the wall cooling, or the ceiling cooling, whatever that is. There are literally thousands of systems. But that's what the additional cooling and the additional heating is meant to do. So that'd be all for today. Let me just open the chat here. So just to make a small, going again quite fast through all of it, all we've seen. And again, this usually takes, or we want to do is to do this on a person, training physically, because it requires, or it can, there are a lot of different systems, a lot of different possibilities, and I've tried to cover the basics. So we've seen some of the most common HVAC systems, AC, underfloor heating radiators, how the thermostatic control works in terms of 2-point hysteresis, PWM, PI control. We've then seen, we've seen the control solutions, the parts involved, the thermostats, and the controllers. And this can be 2 different parts, completely independent, and they just share information through the KNX bus. There are fan coil controllers, and we went through all in box, the specific fan coil controllers, the multi-purpose fan coil controllers, the interfaces that just translate from KNX to some other language, Panasonic language, Toshiba language, Fujitsu language, the thawing, the principles of thawing. So there's an AC unit you have to control, but instead of controlling that directly, you control that with thawing logic to know whether the grills are open or closed or not, and what temperature you want to achieve. The heating valves and the benefits of using electronic relays with the heating valves, because it will last much longer and you will not get the click, 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 click. It's not, if it's an electrical board, you will not hear a lot, but if it's somewhere where you can actually hear it, you might not notice it when you're switching on a light or moving a blind, or the shutter makes more noise than the actual relay. But with a valve, it takes time, it's not making any noise, and you are not actually touching anything. It will be just an action going every 15, 30 minutes, 20 minutes, click, click. So definitely better to use electronic relays with valves. And then a bit of the Zenio thermostat, the inputs a Zenio thermostat has. The inputs are basically the same for both the basic and the advanced, just the special mode would be the biggest difference. Of course, no special modes in the basic thermostat. Differences between basic and advanced, which again were basically the special modes, and additional heating and cooling. That'd be all for today. So any questions you may have, you can post them on the chat, and I'll try to answer them, or my KNX store, Steve, or Paul, or even Vidar.
Thanks, Javier. Thank you again for that. Certainly a long-winded one for you today, so thanks for sticking through it. A lot of technical information, as Mark's just mentioned in the comments.
Yeah, probably is.
Too tech for him, but he's going to go and win some more projects now, thanks to some of that information by the sounds of it. So always helpful. Yeah, I think that is the key. Some of it maybe was a little bit too technical for people. Maybe other people knew a lot of it already, but just to put it in the Zenio world helps. So yeah, no questions, for which is a first. So hopefully it's just because everyone's understood it. But yeah, all good. Appreciate that.
Yeah, thank you very much. I'm just sending tim@myknxstore.co.uk to the chat. That's the email at myknxstore team, so you can contact them for any question, and you've got in the screen support@zenio.com for more if you want to have specific information about the device. But usually Paul himself or his team will be able to answer most of the questions you may have.
Yeah, that's the idea. So the guys know we're around for any help commercially or technically, but when it gets a little bit more tricky, I'll certainly pass it on to maybe Steve and then Javier if Steve isn't unable to, but Steve's got a good working knowledge of the Zenio product set also. Yeah, so I think that doesn't look like there's any questions, but just like to reiterate that at the start of next week we'll do the draw for the free Zenio Z35 for all those that have attended. So one lucky winner will be walking away with the device talked about a little bit today. Look forward to doing that. We'll post a video on social media and stuff, and then obviously contact the winner once that's drawn at random. So look forward to that. I've attended, so I'm not sure if I'm allowed to win, but no. All right, well, never mind. So anyway, we'll get that done. But thanks for attending, everybody. Obviously, a big chunk of time this morning on a lovely day, so we appreciate everybody coming along and getting some extra info on the Zenio range and supporting my KNX store as well by attending. So I appreciate that.
Yeah, thank you very much, everybody. Just just a couple of last words from me. Obviously, we've covered a lot of material. That material obviously doesn't apply to every single project. It's very much project-specific basis. So we have to sort of chip away at each challenge. So if there's anything at all, any heating project you're going into, any air conditioning project you're going into, involve us early on so we can help to spec the right equipment and assist you throughout the project to make sure that we get the right product to do what you need to do and have a happy customer so that everyone gets paid and yeah, move on to the next project. Thanks very much.
Yeah, thank you everybody for coming, and thank you my KNX store for having us here again.
You're welcome.
And looking forward for any upcoming, probably after the summer, in the autumn.
Yeah, we'll hopefully get some old school training in after the summer where we can actually meet people and maybe even shake hands if we're lucky. So
yeah, looking forward to it.
Yeah, good.
I'm actually playing with devices.
Yeah,
live devices on a live rig. There's no substitute for that. That's really important to do.
Absolutely.
Yeah.
This goes a fair way, but it doesn't substitute playing with it and seeing it and actually doing it yourself.
Yeah, exactly.
Yeah, sure.